All right. Hi, everyone. So we're just going to jump right into the lecture. The first thing I want to talk about is hybridization. So hybridization starts with sp, goes to sp2, sp3, sp3d, and sp3d2. Now, how to figure out which one is which, you have to basically count the number of electron regions and then make that equal to the sum of the exponents. So here, there is an understood 1, so that's 2 electron regions. Here is 3 electron regions. Here is 4, 5, and 6. These double marks here just mean repeat what's above. So that it just means regions. And you'll see here, right, 1 plus 3 plus 2 equals 6. Now, what are some examples of these in actual molecules? So for example, if we have carbon monoxide, which looks like this, both the carbon and the oxygen here are sp hybridized, right? And we're not interested in the ones being there. We're just interested in the sp, but we'll say that it's sp hybridized. For sp2 hybridized, you could have something like, I want to keep it all one color. You could have something like an acetone. Both the oxygen and the carbon are sp2 hybridized. Notice around the oxygen that we have 1 region, 2 regions, 3 regions. A double bond and a triple bond both count as 1 region. For sp3, I'm going to draw it out here, we could have the carbon in methane is sp3 hybridized. We can verify that. We have 1 region, 2 region, 3 region, 4 region, right? Each one of those single bonds counts as a region. An example for sp3d hybridized could be PCl5, right? And there are lone pairs around all those chlorines, but that phosphorus is going to be sp3d hybridized. Each one of those chlorines, though, if I did put the lone pairs around it, they would be sp3 hybridized because there are 1, 2, 3, 4 regions. Each lone pair counts as a single region. An example of sp3d2 hybridized could be something like sulfur hexafluoride. I'm definitely not drawing all the lone pairs on all the fluorines, but each fluorine should have 3 lone pairs. Okay, that sulfur has 6 bonds around it, 6 regions, so it is sp3d2. This hybridization concept often shows up as like a free response question and is often 1 point. So it's pretty straightforward. It's a pretty easy point to get. Okay, let's go over some examples of Lewis structures. And while we're doing that, let's introduce the idea of bonding orders. Now, bonding orders really has a lot to do with molecular orbital diagrams. We are not going to talk about molecular orbital diagrams in this class because it's not a part of our curriculum, and it doesn't really help us understand necessarily what's going on with Lewis structures, but it is something that you will definitely see in college if you take general chemistry or organic chemistry, right? But bonding order is pretty straightforward. You just take the total number of bonds, right? And then you divide it by the number of regions. And so we're going to see some examples of that below. BCl3, first thing we have to do is calculate how many electrons there are. Boron has 3. Each chlorine has 7. So 21 plus 3 is 24 electrons. These are valence electrons. Only valence electrons show up in Lewis structures. And our Lewis structure should have exactly 24 electrons. So we put boron in the center because it's the least electronegative. You normally put the least electronegative atom in center. We put the chlorines all around it. We lone pair them up. And there we go. We have 6, 12, 18 lone pair electrons, 20, 22, 24 total. This is perfect, right? The boron only needs 6 electrons. It's one of those exceptions. And the chlorines have to have at least 8. There we go. So let's calculate the bond order here. Bond order, right? I'm calling bond order BO. So the bond order is going to be equal to the total number of bonds. So we have 1, 2, 3 bonds. 3 bonds over how many regions? 1, 2, 3 regions. So 3 regions. The bonding order here is 1. It's the bond order for boron, by the way. And that should make sense because all you see is single bonds. So really, that's the only thing that's going on inside this molecule. Pretty straightforward also. The next example we'll do is triiodide anion, one of Mr. Hicks's very most favoritist molecules. It's such a good one. So iodine has 7 valence electrons. 7 times 3 equals 21. But it's an anion, right? Which means we have to add an electron. Because it's -1, that means we added 1. So we have 22 electrons total in our structure. So if you have 3 atoms, normally just put them in a line, and then start adding your valence electrons. Right, and so let's try and get them to be as close to normal as possible. So here, everyone has exactly access to 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, perfect, right? But is that enough electrons? We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we're missing 2 electrons. So where can we put them? Let's put them on the central atom, right? Now, where does this negative charge come from? If we check the formal charges, let's check the formal charge of this guy over here. We have 1, 2, 3, 4, 5, 6, 7. Iodine's in group 7, so 7 minus 7 is 0, which means that this guy over here also has a formal charge of 0, right? But let's check the central iodine. So we have 1, 2, 3, 4, 5, 6, 7, 8. Iodine is in group 7, and there are 8 electrons in there, which means it has a -1 formal charge. That is where that negative charge is coming from. Okay, so how can we show that? It's pretty easy. You just put a little negative here, right? And that lets you know that that one has a -1 formal charge. Now, let's figure out the bond order for this central iodine. So, there are a total of 2 bonds in the molecule next to that central iodine and 2 regions. Again, we get a bond order of 1. Yes, you can have bond orders that are not 1, and you can have bond orders that are non-integers. We'll see that in just a moment. Let's do carbonate, another one of Mr. Hicks's very most favorite. So carbon has 4 valence electrons. Oxygen has 6. There are 3 of them. And then you see that we have this -2 charge. It's an anion. So we need to add 2 electrons. So 4 plus 3 times 6 is 22, plus 2 is 24 electrons total. Yep. Excuse me. So you put the least electronegative atom in the center, and then you put the other ones around it. Okay, so let's just go ahead and Put all of our lone pairs in. Okay. So how many electrons do we have here? So we have 18 lone pairs on the oxygens, 20, 22, 24, 26. So I have too many electrons currently in my drawing. So what can I do? Well, let's erase some of these and make one of these oxygens a double bond. Now I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24 electrons total. But let's check some formal charges. These oxygens down here have 1, 2, 3, 4, 5, 6, 7 electrons in their possession. The group of oxygen is 6. 6 minus 7 is -1. So each one of these oxygens down here has a -1 formal charge. Now that looks pretty good to me. -1 plus -1 is -2. You can check the carbon and the other oxygen. They'll have 0 formal charges. They'll have a formal charge of 0. Now, let us calculate the bond order of the carbon. So the total number of bonds here is 1, 2, 3, 4. 4 bonds, right? This is a single bond. It counts as 1 bond. Number of bonds. This is a double bond. It counts as 2 bonds. This is a triple bond. It counts as 3 bonds. Now that's kind of confusing because the bonding, like a triple bond, counts as 1 region, but it also counts as 3 bonds. So here we had the double bond, which is 2, plus 2 single bonds gives us a total of 4. 3. Okay, but how many regions are there, right? Because this is regions in the denominator. There are only 3 regions. 3 regions. So we get a bond order of 1.3. Now, what does that mean? It means that these bonds in between the carbon and the oxygen, this bond, and this bond, it means that they're not quite single bonds. They're a little bit bigger than single bonds, right? Think about a number line. You've got 0, 1, 2, 3. This is a single bond, double bond, triple bond. So 1.3 is going to be somewhere in here. It's not quite a single bond, but it's also not quite a double bond. Well, how can that be? Before we answer how that can be, let's think about some other implications of this. So here, let's see. I want to move all this stuff down. Beep, 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 beep. So we've got single, double, triple. So we'll have strength and length. So the single bond is generally going to be your weakest, and the triple's going to be your strongest bond, right? But the length, the single bond is generally going to be the longest, and the triple bond's going to be the shortest. So a bond order of 1.3 means that these carbon-oxygen bonds in carbonate are somewhere in between a single and double bond. So they are shorter than a single bond, right? Because they're a little bit closer to 2, and they're also stronger than a single bond because they're closer to 2, right? Look at this little chart that we have over here. So that's something about what bond orders can tell you. But how do we get bond orders of 1.3? Well, here, let's do this. Delete. We'll do carbonate again. CO3, 2 minus. So The reason why we can have bond orders like that is because of this thing called resonance structures. So resonance structures are just multiple ways a molecule can exist, essentially. So if we draw carbonate again, right? What we can do for a resonance structure, and let me actually, we'll do this bond is blue, we'll do this bond as purple, we'll leave those up there as red. So what I can do for a resonance structure is actually have 3 of these here. And the way that we show resonance structures is we're basically move around lone pair electrons and, lone pair electrons and a single bond from either a double or triple bond. Right? Sounds a little confusing, a little wordy, so what does that actually mean? Well, you'll see that in carbonate we have 1 double bond and 2 single bonds. So let's move some lone pairs and some stuff around. So if I were to take these lone pairs here and make them into a bond, I would kick this bond up into a lone pair. And what that would look like is this. Right? I turned that one of this bond here, I'm going to highlight it. This bond became these lone pairs, and these lone pair electrons, which I'm going to highlight in green, became this bond here. Right? And so now I've got something a little different. Notice how the double bond is no longer in between that oxygen up top. It's now here. Right? And you're like, Mr. Hicks, isn't that the same molecule? You just like turned it to the side a little bit? No, it's different. This is a different oxygen. This is its own very unique oxygen. This is a different oxygen. So how can I get the third resonance structure? Well, I'll take these electrons and bump those down. Sorry, there are too many electrons here. And then I will bump either one of these bonds, it doesn't matter, back up into lone pairs. So these electrons became a bond, which I'm going to draw here. And now we have something that looks like this. I know that was probably a little confusing. We're going to do another example. But essentially, what you need to understand is that this double bond, what color should I use to highlight now? This double bond ends up moving around and is in between each oxygen and the carbon. What's happening, and this is really important, key into this, is that as this molecule is just sitting in reality, it's just sitting there, hanging out, this double bond is constantly moving in between each oxygen and carbon. It's constantly rotating around that carbon. Now, what that means is that since it's happening so fast, right, if you sort of take the average of what those bonds actually are, those bonds really are never quite single, and they're really never quite double either. There's something in between. They are of a bond order of about 1.3, right? Not quite a single bond, but not quite a double bond either. Closer to the single bond, because you'll see that most of the time, more of those bonds are single anyway. Okay, so let's do another example. Here we have nitrate anion. So nitrogen has 5 valence electrons. We have the 2 times the 6 for the oxygen plus the 1 for the anion. We get 5 plus 12 is 17. This is 18 electrons. So we'll put nitrogen in the middle, oxygen, oxygen. Let's lone pair these guys up. Okay, so this oxygen has a formal charge equal to -1. You can prove that to yourself. It's in the 6th group and it has possession of 7 electrons. 6 minus 7 is -1. This nitrogen's neutral. That oxygen on the other side is also neutral. So I show this by putting a little negative charge there. Now, I can draw resonance structures for this. So we have our first structure, right? And you symbolize resonance structures with this double barbed arrow, an arrow going both ways. So what can I do? Like I said, when you're doing resonance structures, you're moving around lone pair electrons and a single part from either a double or triple bond. So let's move this electron, these electrons, let's turn those into a bond. And then we have to take this bond and turn it into lone pair electrons. So it looks something like this. Right? These oxygens are not the same oxygens. This is not the same molecule. This blue oxygen is very unique. So the negative charge was on the left oxygen, and now it's on the right oxygen. Basically, whenever you're drawing Lewis structures, you want to think about taking, like I said, one set of lone pairs and one bond and moving them around. The Lewis structure is always occurring across a single atom. So right here, basically you can think about those things switching across the nitrogen. Up here, they were all switching across the carbon, right? That double bond was kind of switching across the carbon. So let's do another example. Example 3, SO2. So we have 6 times 3 equals 18. Both sulfur and oxygen are in the same group. So they both have 6 valence electrons. So we have sulfur, oxygen, oxygen. Very similar example, right? And so let's draw our Lewis structure. So take one of these lone pair electrons, slam them down, turn them into a bond, but then we have to get rid of a bond somewhere. We have to move 2 things. So we'll take this bond and we'll turn it into lone pairs. So this one right here was turn lone pair into bond. And this one here was turn bond into lone pair. And so take a second and try and draw what this would look like now. You have oxygen on the left now with 3 electrons, a single bond to the sulfur. And now we have this sulfur doubly bound to this oxygen, which only has 2 lone pairs, right? We're just moving things around. Think of it as sort of like a book. These lone pairs come down first, and then they have to kick this single bond out and turn those into lone pair electrons. Okay, let's see, what else is there? Okay, so what is the bond order for sulfur here? Beep. So the total number of bonds in both of these resonance structures is 3 bonds, because I've got the double and I've got the single bond. So it's 3. A double counts as 2. So 1, 2, 3. But how many regions do I have? I only have 2 regions. So this ends up being 1, 2 goes into 3 one time with 1 left over. So this is 1.5. So we think about that number line, we've got 1, 2, 1.5 is exactly in the middle. 1, 1/2. Right? Remember that 1 1/3 was not in the middle. This makes sense because half the time the bond order, or half the time the sulfur has a double bond on one side and half the time it has it on another side. So it's like halfway to a double bond, halfway not to a double bond. That would be the same thing for this nitrogen up here. Okay, let's do our final example, which is example 4, ozone. Ozone is O3. Ozone. Yes, the stuff in the sky that protects us from the sun. Oxygen's in the 6th group, so it has 3 times 6 valence electrons, which is 18 total. We have oxygen, oxygen, oxygen. And I believe it looks something like this. 2, 4, 6, 8, 10, 12, 14, 16, 18. Yes. Okay? Now you're like, whoa. Wait a second, Mr. Higgs. Let's check out these charges. So the formal charge for this oxygen is equal to -1. The formal charge for this oxygen is equal to +1 because there is 1, 2, 3, 4, 5 electrons in its possession. 6 minus 5 is +1. This formal charge is going to be 0. -1 and +1 equals 0. The molecule is not charged, so that makes perfect sense, I suppose. Now let's draw some some resonance structures here. So let me make a copy of this dude. Copy, paste. Okay. Now what I want you to do is try and draw the resonance structure here. Now be careful. You may be thinking, I'm going to take these electrons and turn them into a bond. Okay, so then that would look something like this, right? But remember, when you take one lone pair and you crash it down, on the other side of whatever that atom is, you have to take that bond and kick it up as a lone pair. You can't do that because then you'd break that bond. So you're like, well, then what do I do, Mr. Higgs? Well, you have to go the other direction. Notice how in each of these examples, we do nothing with the central atom. It just sits there. It's sort of what everything is going around. So I'll draw your arrows here. Those become that bond. We have to kick a bond out. Every time a lone pair forms a bond, you have to kick a bond out as lone pairs. So see if you can draw what that looks like.